Hello, a great welcome to the series on Abaqus. Myself, Jarajan P. This is tutorial number 2 and explains analyzing a simply supported beam using Abaqus. This tutorial is split into two parts, part A and part B, to improve the visibility for the users. Now, the part A covers the definition of the various modules such as parts, property, assembly, step, load, mesh, and job. Whereas the part B include running the analysis, discussion on a visualization module, and finally the interpretation of the results. So let us first read the problem statement. So as you can see, shown is a simply supported beam subject to a triangular load. So the span of the beam is 6 meters and the triangular load has got an amplitude of 10 km per meter at the right end, whereas it is 0 at the left end. The span of the beam is 6 meters and the cross section of the beam is shown here. The material is steel. The width of the cross section is 50 mm and the depth is 200 mm. The property of the steel material is E is equal to 2 into 10 raised to 8 kN per meter square and the Poisson's ratio is 0.3. Now let me just highlight one very important thing before switching to the Abaqus. Obviously, in future we will solve problems in different areas including mechanics of solids, steel and concrete structures, structural dynamics, earthquake engineering, geotechnical engineering, soil dynamics, and geotechnical earthquake engineering. Now, though this tutorial takes about say one hour or 1 hour and 15 minutes, don't get worried. This is a very simple problem which you may be able to complete just in 5 to 10 minutes time, not more than that. So please start practicing. So practicing makes the man perfect. So let me take you to the Abaqus. Okay, now you are in Abaqus. So before starting the model, we will set up the work directory. So go to the file, set work directory. So here I have set the work directory as a C Abaqus tutorial. Okay, so remember that when the model development is in progress, Abaqus go on writing the different files to this work directory, and also when the model is run, various output database files are also written to the same folder. So just press it OK. So let us just save this file in the same directory. So save as. So we'll go to Abaqus tutorial. Okay, so we'll save it as SS beam CAE. Okay, so it was already there. Okay, I will write it. So now on the top of this title bar, you can see that the name of the work directory. Okay, it is clearly visible to you, and also the name of the file also you can read. That is a model database, right? CAE with an extension of .cae. Now please remember that Abaqus do not have any system of units. The user can use any system of units. He can use kilonewton meter, Newton millimeters, kilonewton centimeters. Only thing is that he has to use it consistently all throughout the analysis, right from the beginning to the end. Okay, so let us start developing the model. So obviously the model has to be developed in this particular order only as given in the module list. It does mean that first we will develop the part, we will mention the properties, create the assembly, then we will define the steps. If there are any interactions, we will provide details of it, apply the loads, do the meshing, go for the optimization if required, create the job, run the analysis, and then inspect the results in the module. So let us start with the first one, that is the part module. Okay, so when you switch to the part module, you will find that the toolbox here has changed. Okay, so let us first start creating the part. Okay, so you can press this create part. Okay, so in part you have to give the name of the part. Ensure that you give a name so that you can easily identify it in all your future operations. Okay, here our model is very simplest one, so I'll just give it as a beam, and basically it's a 2D problem, so you can select it as a 2D planar. It's a deformable. Okay, and the beam elements do have a base feature known as a wire. So please select it. And here the span of the beam is say 6 meters. So the approximately the sketcher will have a sizes of 10 meters. So this do not have much significance, but it is better for you so that you see that the entire sketch is within your ambit of view. Okay. So now you will find that the sketcher appears wherein it has got the look of a graph paper, and this is the origin of the sketcher, and you can start developing your sketches. So in the present case we have to just draw a beam which is 6 meters long. Okay, so the beam can be simply drawn using the create lines option. Here you will find that there are many items available which we will see across the other tutorials. So here we'll just press create line. Okay, so I want to have my starting point at the origin, okay, of this sketcher. So just press here, and obviously it will have the other end as 60, and we are in the xy plane right now. So okay, so you'll find that yes, the beam is already drawn. Okay, you can just okay, yes, this is my beam. Okay, so this is the end point, and this is the start point, and this is the end point. Now remember we have set the size as a 10, so this is a 5 meters plus 1 meter, so that's it's going a little bit out. Okay, so that's not a matter at all for us. So we completely sketch the beam. So you can just look into the prompt area. It asks you sketch the section for wire, whether the beam sketching is over. You can say the yes, done. So this means that we have successfully created our part, and the same part you can see in your model tree as well. Go to the part 1, you can see that yes, you have got a new part known as the beam. So and you have got many components of that particular item. One is, for example, the features. So here you can see that the feature, yes, wire 1. Okay, so it's a wire element is a feature associated with the beam element. Okay, so the part is over. We can go to the next module, the property. Okay, so in property module, whatever needs to be defined, it again varies with the type of the problem. Or in this case, you have to define number 1, as is already clear from your module name itself. You have to define the property, and in Abaqus the sequence is something like this. You define first of all the property, okay, then you assign this property, to a section, and finally you assign this section to a member, right? So from property, assign this property to the section, and finally assign this section to the member. So let us start defining the property. So click here, so create material. Obviously you know that the material, we have got only one material, that's the steel. So for easy identification I will just give it as a steel, and here straight away go to the mechanical. Here you will find that two parameters are that of interest to us is elasticity and plasticity, because it's a conventional problem. So here we will not use any kind of parameters. We ensure that the beam essentially remains elastic only. Our loading is like that, it remains within the elastic region only. So in this problem we will define only the parameters associated with the elasticity. So in the elasticity, select the elastic, okay, and then here you will find that the other parameters, the type, you can have the isotropic and isotropic. Here we'll obviously select the default one, isotropic, and you can start providing the parameters to define the elasticity. Obviously we know that two parameters are required, Young's modulus and the Poisson's ratio, and the Young's modulus will enter it 2E8 and ensure that we use the same unit, because here I am using for the load kilonewton and for the length I am using meter. So I have specified my Young's modulus in 2E8, that is in kilonewton per meter square. Okay, and the Poisson's ratio is dimensionless 0.3. Okay, so we defined one property known as C. Okay, fine, fantastic. So we defined the property. Now let us go for defining the section. So in the property module, remember, in addition to property, you have got defining the creating the section. Okay, so press this create section. Okay, so here for easy identification I will say it's a section beam. Okay, I can easily say that. Okay, and ensure that you choose the right category. There's a beam here and the type also beam. So continue. Okay, so now go on reading this. So beam shape. So here is a place where you can give the description of the beam profile. So right now we have not created any section. So let us create it now right now. So on the right side you will find that there is a create beam profile. Okay, so just press it and you can assign a name. Okay, here one section, but in spite of that, give the name as profile beam so that we can easily identify it later. Select the rectangular one. We know that is our cross section is rectangle. Okay, continue. Now you can see that yes, so this A and B are nothing but these are the length and the width of the or rectangular cross section. So you can give say A as say it's a 50 mm. So 50 mm means that it is a 0.05. Okay, and B as we can give it as a 0.2. It's a 200 mm, so 0.20 meters. So okay, fine. So we have defined our profile name through the profile beam section. Okay, fine. Then look into the material name also. We have generated the steel property that we have assigned to this. Okay, now press OK button. So this means that we have created first the property, then we assigned this property to our section. Okay, now this section needs to be assigned to our beam member. Now here is a one assigned section. Okay, so you assign the section, so it will ask you select the regions to be assigned. So obviously this is my beam to which I need to assign the section. Okay, once the section is over, press the done button. Okay, now look here, the section that we are assigning to this beam is a section known as a sectional beam that is already generated. And read here that the right material is also assigned, that is the steel. So okay, we are fine. Now as you can see, here we have the beam that is represented by a line. How do we know that the cross section is properly oriented or not? That is important to us, right? So now let us define one more parameter known as the beam orientation. This is for the beam orientation. Okay, so just press it. Okay, it will ask you select the regions to be assigned a beam section. So this is my section. Okay, so we have select the region, press done here. Now here it prompts you enter an approximate n1 direction. That is, what is your one direction? So here it is already by default, it is indicated by an arrow. So my positive one direction is along this direction towards the right. So it's acceptable for me. So this is my one direction. It does mean that the normal will be the two direction. Okay, so just enter it. So here you can see that yes, this is my one and this is my two. So one and two directions are already defined now. So it asks me click OK to confirm the input. Okay, for me, no problem. Now look here. Now you will find that, okay, let me just go to before that, because you may see that how this has come just like that. Okay, so as you know that we have assigned also the orientation. This is my one direction and this is my two direction. Okay, now for the major structural members like the columns, the beams, etc., it is important that the cross section is properly oriented. Okay, that means the B dimension and the D dimension, it is associated with the section in the right way. Okay, it is not interchanged. So how do we check whether the width and the depth are properly reflected in our model? Because right now I am not seeing any cross section. I'm just seeing a line that is representing a longitudinal view of my model. I want to see what will be the cross section. So what you do, there's a way out. Go to the viewport, and in the so I think yes, go to the view. It's not to the viewport. Go to the view, and in the view there is a parameter or there is an option part display options. Just click it, and in the part display options go to general, and there is one last parameter idealization. render beam profile. Just click it, okay, and apply. Now look here. Now you will find that yes, this beam is associated with, it is also showing say a cross section for me. Now how do I show the cross section? Because this is my XY plot. You can just go to this, that is isometric view. Now in the isometric view, you can just zoom it, okay, and you can just translate to see the cross section. Yes, so the depth, the larger depth, and you are having the 50 mm width and the depth. So if you find that the dimensions are interchanged, you have to go to it. Now the present case, it's all right for us. Okay, so this is how you should check the cross sectional orientation, and it's a very important part because we know that the calculation of the stresses, the calculation of the deflection, etc., it depends upon the section orientation. Okay, fantastic. So what you can do is that you can go for the XY orientation, and what you can do is that to keep back, go to the back view part display options and just untick it, uncheck it, apply, okay. So this means that in the property module we have defined the property, we have defined the section, we have assigned the section, and we have assigned the orientation. Fantastic. So you will also see that whatever we did in the property module, it is getting reflected in the model tree as well. So here for example, you will find that yes, a new material is being added to the steel, known as steel is added to the model tree, and you also find section is already automatically defined, a profile is also written to the model tree. Means that when we start working in this viewport area, you'll find that whatever details are being added, it is automatically getting populated in the model tree. Okay, so the second module is also over. I think that the other parameters are of not of any use right now. We'll see it obviously in other tutorials. So property is over. Next we can go to the assembly. Now what is assembly? Basically, if you see the Abaqus first generate the parts. Okay, as I already explained in the introduction tutorial, for example, if you're having say for example a column and a beam, you can develop parts known as a beam and then another part known as a column, and in the assembly module we just assemble these parts, right? Assemble these parts to their right and orientations and create the entire structure which we call as the assembly. In the present case, you know that we have got only one member, so assembly is not a big issue at all. So what you need to do is to create the assembly is, here there is a button on as create instance. Okay, so what we are doing in the module assembly is we create an instance of a part. So we can have multiple instances of a part. So in this present case, we have got only one instance, that is a beam. Okay, so just press it. So create instance. So when you press instance, this is the create instance dialog box. Create instances from parts. Yes, I want to create it from parts. And you know that I have got created only one part known as a beam. And here instance type. This is very important. There is a dependent instance and also an independent instance. The basic difference between these two is that as far as the dependent is concerned, you will mesh that particular part in the part module, okay, in the part, and then you cannot mesh it in that assembly module. On the other hand, if you take the instance as independent, you will not be able to mesh it on the part menu. You will be able to mesh it only in the instance, only in the assembly. So here I have selected dependent mesh on part. So this is, I think, that the most obvious choice for many of the problems. Okay, so here is an auto offset that is not relevant to me. I will just apply okay. So now you will find that yes, the beam member is appearing and you are in the assembly module. Okay, and here you will find that the color of this member, it has changed, it has changed to the blue color. Okay, fine. So now what is important is the assembly is over. We don't have anything over here because this is a simplest structure we can ever have. So from the assembly, now we can go directly to the step. Now when you go, sequentially as per this list shown here module. You ensure that yes, all the input parameters are provided to the Abaqus, okay, properly. Now step. What do you mean by a step? In Abaqus, a step means it's an analysis step, right? So the step module allows you to define, okay, perform the analysis in the various steps, okay. And basically, if you look into Abaqus automatically creates a step known as initial, right? And this step known as initial you will not be able to change or modify, okay. And you can create all other subsequent steps after this default initial step created by Abaqus. Now why Abaqus creates initial? So that all the important other parameters such as the boundary conditions, then for example the interactions, etc., you can define in this initial step, and then you can apply the load in the subsequent step, okay. So now, so in the step menu, obviously as usual you will find that here we have the create step. So you just press the create step, okay. So you let us create the analysis step. So I'm just creating it as a step beam, okay. And please read this properly. Insert a new step after initial. So you will be inserting this new analysis step with the name of a step beam after the initial. And here is a very important step, that is a procedure type. It asks you what kind of analysis procedure you are going to implement in this Abaqus module. So now here is a, you know, that's a simple static problem. You can just select static general. You can see that there are many analysis types available here because Abaqus is a general purpose software. So here I am selecting the static general. So you can just continue. When I say continue, it does mean that you need to provide some more parameters, okay. So continue, okay, fine. Now here you will find many parameters known as the basic, incrementation, other, etc. And these parameters are at least not relevant to us. So anyway, I just want to tell you one parameter known as NL okay. This parameter will take care of accounting for the nonlinear geometric effects. Okay, what are these nonlinear geometric effects? Obviously, you know that in some cases we know that the excessive or larger displacements are likely to have a critical effect on the other stress resultants or on the behavior of the structural member. In which case, it is important that you keep NL geometry on. So this is obviously not a large displacement problem. So I keep NL geometry as off. And all other parameters are not of much importance to me as far as this problem is concerned. So I just keep it as okay. Okay, fine. So I have generated my step. Now please remember, on the right side you have got a menu known as a manager. For example, when you create a step here, you can also go to the step manager. Go to the step manager. Look here. Now you will find that yes, there are two steps here. One is an initial step, okay, which is automatically generated by default by Abaqus. Okay, you cannot change it. And you have generated another step known as a step beam, and the analysis procedure is static general, and the nonlinear geometry effect is off. So suppose you have changed your mind, you want to change, for example, this as on. So what you can do is that you can just edit it, okay, and you can just change it. Okay. So anyway, I'm not going to change it. So the manager can be effectively utilized, okay, for many operations, such as, for example, you want to edit the in parameters, if you want to delete it, or you want to rename the step, etc., you can use it, okay. So my step is over. So let me just see whether there are any parameters that is relevant to this, because it's the simplest tutorial I have taken to start with. So step is good enough. Now interaction, I got to one element only. I don't have any kind of interaction, which you will see other contact problems. So now we can straight away go to the load. Okay, so go to the load. Now in the load, don't be under the impression that you are defining only the loads. We essentially define basically two important things. One is the boundary condition, and the second one is then we apply the loads. Okay, fine. So first, obviously, before proceeding for the load application, ensure that the boundary condition is applied properly. So to apply the boundary condition, go to this second button, that is you can read it, create boundary condition, just press it. Okay, create boundary condition. So for example, you can say that it starts with BC. BC means it's a boundary condition. I'm just writing it as a beam. Okay, beam. And it's normally the boundary conditions we attach it with the initial step. Okay, fine. So what you do is that you go to this initial step. Okay, fine. So then go to the category mechanical, then displacement or rotation. Okay, fine. So then what you do is that you continue. Okay, it asks you select the region for the boundary condition. So obviously we have the two boundary conditions, one for the pendant and one for the roller end. So go to the pendant, okay, select it, then you have selected done. Now you can apply the boundary condition. At the pin, obviously you know that the two displacement components are restrained. That is your displacement component in the one direction and two direction. That is x and y components. So you just select it. So we have restrained it. So u1 and u2. Okay, we have restrained it. Okay, that's okay. So you can see that yes, the boundary condition is rightly applied here. Now if you remember, we have given a boundary condition known as a beam. So you can also change it. For example, right here itself, you can go to the boundary condition. Okay, you can press it. You can see that yes, we have generated a boundary condition. You can BC beam. So you can just rename it BC. I'll keep it as this is a boundary condition corresponding to the pendant. So I'll keep just do BC pint. Okay, so that's okay, fine. Okay, so you'll find that yes, BC pint. So you'll find here one very important activity. So BC pint, it is created in the initial step and it is automatically propagated to the loading step. So this you need to read this line also very carefully. Okay, and you can also activate, deactivate all this, propagate, and or you can make it inactive also. You'll see it in some other examples. So we created one boundary condition known as boundary condition pint. Now if you remember, we need to create also one boundary condition corresponding to the roller end. So again what we do is we go to the create boundary condition, and in this case I'll just say for my easy identification as BC rolled. Okay, fine, BC rolled, and obviously I will create in the initial only mechanical displacement rotation, select the same, continue. Okay, it asks you select the regions for the boundary condition. So importantly, for the beginners, you have to start reading this thoroughly and proceed as per the instruction given here. So this is my end corresponding to the roller end. Select it. So after selection, press the done button, and you know that as far as the roller end is concerned, u1 is a free, okay, and u2 need to be restrained. Why is to be restrained? Okay, fine. So now in the boundary condition, if you will go back, you'll find that yes, we have got two boundary conditions known as BC pinned and BC rolled, and both are created in the initial step and it is propagated to the loading step. So having done that, look here. This is my boundary condition, the graphical representation. This is also a boundary condition. Okay, fine. Now it's the time we go for the application of the load. Okay, it's a very simple problem. So for that, what you do is you go to this create load button. Okay, fine. So create load button, and again what I do is I say load beam, or I can say that load. I might is a triangle loading. Okay, load triangular. Okay, just for easy identification. And remember, any load is to be created in the corresponding analysis step. So obviously we know that here the analysis step is the step B. Okay, so then category is mechanical. Now we know that ours is a triangular load. So Abaqus provides you various types of loads, for example concentrated moment, pressures, pipe pressures, body force, gravity, many things. So we can choose the line load here. So just continue it. Okay, continue. Okay, fine. Now read the prompt area, select the bodies for the load. Okay, I want to ensure that yes, the load is applied. Okay, the load is applied here, that is in this member. Okay, so just select it, done. Okay, now you can say that yes, the name of the load is load triangle, and you have selected a line load. and we are applying this load in the step beam analysis step. Okay, global system and distribution, obviously we know that this is not a uniformly distributed load. Okay, and so we need to define it through an analytical field because it's a line load, it's not a uniform one. So on the right side of this uniform button you will find something written as effects. So this is for creating an equation that represents this line load. Okay, creating the variation of this line load. Okay, so just press this analytical field. So I will say that this analytical field, I will call it as analytical field for my beam. Okay, so expression I want to provide. Okay, now look here. So here you can write down the equation. So now you know that it is basically is a triangular load. Okay, at the start its value is 0, at the end its value is 10 kilonewton meter. Obviously we know that this can be represented by a simple equation y equal to mx. The slope of this line is nothing but say 10 by 6, that is equal to 1.667. So just to type it, don't write any equal, just type it 1.667, okay, into x into and use capital X. Okay, so here we have indicated or instructed Abaqus how your line load is going to change. So it is a linearly increasing 1.667 being its a slope and x. Okay, so that's good enough. Okay, fine. So now in the distribution, replace this uniform by the distribution that we have already defined. Yes, this is analytical field beam that we have just now created, the field variable, and now the component. This allows you, is there any component of this applied load in the one direction, that is in the x direction? No, I don't have any component in the x direction, and in the y direction obviously it is in the downward direction, so I can just write as -1. Okay, so I'm not talking much about that, we will see it in the other tutorial. Okay, okay, so look here, now you will find that yes, the triangular load is already defined. Okay, it has got intensity of 0 at the start point, the maximum at the edge. Okay, so this means that our load module is also over. So the load is over, the boundary condition is also over. Now we can go straight to the mesh. So we are going very systematically, okay, step by step. So this ensures that we don't miss any input variables. Okay, when you become an expert later, okay, you will be able to okay, switch from one to the other very easily. Okay, so we'll go now to the mesh. Now let me just tell you, based on my experience, meshing is one of a very important input operation as far as an Abaqus model is concerned, because it is by just into the meshing you can just make a conclusion whether this model is developed by an FEM specialist or by a common man, because in the accuracy of the Abaqus results entirely depends upon the meshing procedures, okay, the element type is selected, okay, and also how what is the strategy, okay, that you have adopted in performing the meshing operation onto a global part or to a local part. So in this case, our beam element is a simple element. Okay, so we need not to break our head in the meshing. It's a very simple procedure. So I'm not going to tell you a much detailed explanation of the various parameters here. What you need to do is that go to the seed part instance. So here you will find a term known as a seed. Seed means it is what is at a distance, how you should an edge in the formulation of the mesh. Okay, so here there are two seeds. One is a global seed defined by this button, and also suppose that you want to refine one particular edge, thereby you want to define a local seed, you have to use this seed edges button. So the first one is a global seed. Okay, and remember that you want to seed part. Okay, so now just press it. Yes, look here, now you get a message, dependent part instance cannot be edited. So means that you will not be able to create a mesh in the instance. This is what we have already informed the Abaqus. I will be doing the meshing on the part. So what you do in order to avoid this is straight away go to here. Right now you're in the assembly, go to the part. Okay, now there will not be any problem. So press this button. Yes. So now you know that this is meter span, right? So I have decided, okay, I will divide this entire beam into say 10 centimeters. This means that I will just keep it as a 0.1 meters. Okay, that should be good enough for me. So you can just apply it. So you will find that yes, this beam is divided into small segments of each of 0.1 meters. Okay, and before pressing OK, just press apply and see how the seed parameter looks like. If you see that this is wildly spaced, you can change it. If you find that this is too close, you can again increase the value. And once you are satisfied, you can press OK. So means that my this seeding is over. Because before you go for the meshing, ensure that the global seeds, local seeds are defined. Then there is one thing known as assign mesh control. Now this mesh controls means that the various, Abaqus has got a various mesh control techniques. It's got free meshing, then it has got a structural meshing. Many type of meshing controls are available, meshing control algorithms are available. So let us, we don't have, just a 1D element. We need not to worry about this mesh control algorithm here. What you can do is that you can straight away go for the assignment element type. So this is very important because every analysis, every model need to have the right kind of the element. So here what you do is that you press this assign element type. Okay, it asks you select the regions to be assigned. So just select this. Okay, this is a beam. So done. So now here you will find that there are many things. So element library, select the standard, and family, it's my beam, and geometric order. And here you will find that there are two things. One is a linear and quadratic. If you have undergone a finite element course, you will find out what is a linear order and what's a quadratic order, and all that we will see later also. Okay, and in the beam type, what I will do is that we are interested in the shear flexible nature. So shear flexible type we will see. Okay, and look here, this is the element type. This element is known as a B21 element. B21 element, which indicates that it is a two node. It's a two node. It's a two node linear beam. Okay, because we have selected a geometric order of linear in a plane. So our element is known as B21. So that is okay for me. Okay, so remember that before proceeding for meshing, you have to set the global seed. If local seed is available, that also you have to set. Okay, you have to set the mesh control that is not applied in this particular problem. Then you have to select the right element. Okay, and also there is also known as a verify mesh. This is just to ensure that yes, the mesh do not have excessive aspect ratio, or it do not have what we call as very small angles, acute angles, or excessive angles, large angles, etc., which affect the calculations. Anyway, those are not applicable for here. Here I am not going to do any kind of a verify mesh also. We'll see it in other examples. So once all these are over, now we can proceed for the mesh. So this is the button for the mesh part. Okay. So once you press it, it asks you okay to mesh the part. You can say that yes. So this means that the meshing is complete. Okay. So you can see that here bottom it provides you the message area. 60 elements have been generated on the part. Why 60? Because we have selected the spacing as 0.1 meters. So we have got 6 meters means it has generated 60 elements for us. So this means our meshing operation is also over. Okay. So now it is the optimization is not applicable for. Now we can straight away go for to the job. So before submitting this analysis model, what we need to do is that we have to create a job model. Okay, so I'm creating a job here first. So I'm writing job beam. Okay, so let me just use a small letter job beam. Okay, fine. And I'm using the model. My model name is model 1. Okay, because you know that see, you can create a job either from a model or from an input file. Here I want to create the job from my model only, and the model name is model 1. So continue. Okay, fine. So it does mean that, and you can keep all this default option. That means I want a full analysis, and run this in the background and submit it, okay, immediately. Okay, so we have uh, we have created the job. So the next step is that we need to submit the job. Okay, for running you need to submit the job. Now before proceeding for submission, I think that we have left out a very small part. Go to the step. In the step module there is one more parameter. I think it is in the step module only. Yes, see, when you run the Abaqus, okay, obviously you want to inspect some variables, right? For example, as far as the beam in the present tutorial is concerned, you would like to investigate how your shear force changes, how the bending moment changes, okay? And for example, what's the variation of the deflections or the deformations, and how the reaction forces are changing. And because after an analysis, Abaqus writes thousands of variables, okay, and many of the variables are not of interest to you. You want to inspect only some variables, or only some 2 or 3 variables are of interest to you. So Abaqus allows you to specify these variables in the so-called, look here, this is where create field output. Field output creation means you can ask Abaqus, I am interested only in these variables, okay, and please write only these variable to my output file. Okay, so means you can create the field output. Now field output, I will say that, remember that creating the field output should be done in the step module. Okay, we have forgotten it. Okay, we can do it right now. So f output beam, okay, and it is in the correct analysis step beam, and the procedure is static general. Continue. Now here you will find that there are many things. So you will find that, for example, yes, stresses, strains, displacements, forces. So means that stresses itself, you have got many type of stresses. Now as far as this tutorial is concerned, I am interested only in the forces or the reactions. Okay, forces in the reactions. And here when I selected forces and reactions, you will find that Abaqus has selected many variables. Maybe that some of the variables are not of interest to you, or maybe that I am not knowing this. So let us just expand this. Okay, now you can just select whatever is required for you. For example, I may select a reaction force. You may not require this also, but I will select a reaction force, reaction force and moments, RT, RF and RT, and or what you can do is that you can just deselect it. I am not interested in any of these things. Okay, so instead what we can do is find that there are many parameters here. So look here there is one parameter known as nodal forces in beam section orientation. Select that. Okay, that is a N for CSO. I normally call it as N for CSO. That's the nodal forces in the beam section orientation. This, if you have identified this as your output, then Abaqus will provide you a variation of the shear force, a variation of the bending moment, everything. Okay, so all these things, I don't want any of these things. Okay, so I will just deselect. So now you will find that we have reduced the size of the output file. Okay, so we have selected only one, that is a N4 CSO, nodal forces in beam section. And if we have selected the field output, then now we will be in a position to see the shear force as well as the bending moment. So this is okay for me. Okay, now we are in a position to go back to our job and run it. So go to the job and select this. Okay, so now we can start submitting the button. Okay,